Hi, and welcome to Dr. V's Chemistry Webcast. It's me, Dr. V, and I'm here to talk about periodic trends. Specifically, I want to talk about trends in ionic radii. Here's what I'd like to accomplish in this webcast. First, I want to review cations and anions. Hopefully you remember this, but just in case, I'll go through it again. And then I'd like to compare the radii of ions to their parent atoms and state the period and group trends that we observe for ionic radii. And explain why these trends occur as we go. It's not enough to just know the trends. You need to know why, and then wrap up with some practice problems. So let's start by reviewing ions. There are two broad categories of ions. We've got our cations and our anions. Now, I hope that these are familiar terms, and they probably are, but just in case, I'll go through them very quickly. Cations are positively charged ions because a species has lost one or more electrons. An example would be lithium ion. And anions are negatively charged ions because the species gained one or more electrons, and an example would be oxide ions. So, what we need to remember is that atoms will gain or lose electrons to end up with an electron configuration that matches that of a noble gas. It's isoelectronic. It has the same number of electrons as a noble gas. That's going to leave you with a species where all the sublevels are completely filled, no partially filled sublevels. And you'll have 8 valence electrons, which is really very stable. We see a lot of stability with this. So typically what we see are that metals lose electrons to form cations, nonmetals gain electrons to form anions. All right? It's all about getting to the octet rule. So we can use this to predict what typical charge we might expect for a particular element when it forms an ion. Let's look at cations and neutral atoms and compare them. So I've got some depictions of some metals here. We know metals typically form cations by losing electrons. All right, and so the yellow spheres are representing the patterns of their atomic radii. And now let's look at the ionic radii, which I show in blue. All right, well, what you see, it should be very obvious, is that the blue ones are much smaller than the yellow ones. Typically, cations are significantly smaller than the parent neutral atom. So that's what we need to remember here. Cations typically have a smaller radius than the parent atom. Why? Well, again, we always need to know why. It's not enough to know the trend. Cations have fewer electrons than the parent atoms, which means there are fewer electron-electron repulsions, so they don't have to spread out quite so much. And in fact, because of the loss of electrons, you may have actually lost occupied sublevels or occupied shells in the electron configuration, in that structure of the atom to form the ion. And so the electrons that remain are in sublevels that are closer to the nucleus. They're closer to the nucleus, so they have stronger Coulombic attraction to the nucleus. Always comes back to that, right? Coulomb's law. We keep talking about it in this unit. Now let's go on and look at anions. All right, so here are some neutral nonmetals. All right, they're in yellow. They're the neutral atoms, and we can see their radii. And let's look at the anions. Wow, the green ones, they're quite a bit bigger, right? Sometimes more than twice as big. It varies, but it's substantially larger, those anions. So let's go on and talk about this. All right, anions typically have larger radii than the parent atoms they're made from. Why? Well, they've got more electrons than the parent atoms. All right, so that means I'm going to have more electron-electron repulsions, and they're going to spread out a little bit more to try to minimize those repulsions. And I've got no additional energy levels, so that's what we've got. So now let's talk about the trends. All right, as we go down a column, what we see for both cations and anions is that the ionic radii increase down a column. Why? Well, I've got more occupied energy levels. These energy levels are farther from the nucleus, and therefore those electrons experience a weaker Coulombic attraction to the nucleus as we go from oxide to sulfide to selenide, etc. It's true for the metal cations. It's true for the nonmetal anions. We're all good. All right. It's the same pattern, actually, that we saw for our atomic radius trends. Now, if we talk about the period trend, it's a little bit more involved. Same basic patterns, same essential reasoning. All right. So if we look at the cations, they get smaller. As we go from sodium to magnesium to aluminum ions, we do see that they get smaller as we go from left to right, because they've got a stronger nuclear charge, a larger nuclear charge, so its outermost electrons get held more tightly. And then we have a big jump to the anions, and then they get smaller. All right, for the same reasoning that we saw before. We've got that increasing nuclear charge holds the outermost electrons more tightly, stronger Coulombic attractions between the nucleus and the outermost electrons. We're feeling the same energy level as we go across. All right, and so that's what I said before. The outermost electrons have that stronger Coulombic attraction. It keeps coming back to Coulombic attractions and understanding atomic structure. Which of the following would have the larger radius? So let's do a few practice problems. Just some simple comparisons. If I'm comparing calcium atom or calcium ion, which would we expect to have the larger radius? I would expect calcium atom to have the larger radius. Both species have 20 protons, but the calcium atom has more electrons than the calcium ion, so it would be larger. If I'm looking at the phosphorus atom or a phosphide ion, I would expect the phosphide ion to have the larger radius. Both species have 15 protons, but I've got more electrons in the phosphide ion. If I'm looking at the calcium ion or the chloride ion, this one's a little harder than the other two, right? But it's still doable. What we have to remember is that both species have the same number of electrons. I would expect chloride to have the larger radius. Why? Well, they both have 18 electrons, but calcium has 20 protons, where chloride has 17 protons. 17 protons won't be able to hold those 18 electrons as tightly as the calcium ion's nucleus can, and that's really what it comes down to. All right, let's do a few more. If we have the potassium ion or the scandium ion, I would expect the potassium ion to have the larger radius. Both have 18 electrons, so again, isoelectronic, but the potassium ion has 19 protons versus 21 protons for scandium. If I'm looking at chloride ion versus iodide ion, I would expect the iodide ion to have the larger radius. Iodide has more occupied energy levels than chloride, right? It's in a lower period. If I'm comparing the phosphide ion or the sulfide ion, I would expect the phosphide ion to have the larger radius. Again, both species are isoelectronic. They both have 18 electrons, but phosphide has 15 protons to hold those 18 electrons versus 16 protons. For the sulfide ion, the phosphide ion would be bigger. Okay, I think we're ready to wrap this up. Let's do a quick summary before we go. All right, cations have smaller radii than the parent atoms. Anions have larger radii than the parent atoms. All right, ionic radii increase as you go down a column, but as you go from left to right across the period, the cations get smaller, and then we have a big jump, and then the anions get smaller. I hope you found this helpful. I encourage you to subscribe to my channel. I keep making new videos. I want you to learn more chemistry.